Hello everyone, this is Jitendra Vata presenting my research on the seismic performance of precast cladding panels with rocking connections. With the advent of framed structures, the skin of buildings started to be separated from its main structure. The transition from the load-bearing walls to curtain walls partly arose from a challenge of creating tall buildings while maximizing the rentable floor area. The main function of cladding systems or curtain walls is to isolate the interior of the building from the external factors to create a comfortable domain for living and day-to-day functioning. The precasting process allows greater quality control, which also enables better surface finishes to the buildings. The early high-strength concrete dramatically reduces the curing time, which allows mass production of precast units in different shapes and sizes. The precast units incorporating glazing units within themselves avoids the need of external framing as those of the traditional curtain wall system. One of the most important features or characteristics of precast concrete panels is its fire resistance capability. Nonetheless, the precast cladding system is characterized by the connections in the seismically active zones, where the top connections may be of horizontal slots or of ductile rods, and the bottom connections are generally fixed to the structure. The isolation between the panels and the primary structure is provided either by sliding of poles connecting the panel and the structure within the slots, or by flexing of the ductile rods. Another important aspect of the cladding systems are the joints between the panels, which are generally interposed using sealant. A larger vertical gap between the panels is provided at building corners to avoid pounding between the panels during earthquakes. However, in real practice, the bolts may not be exactly at the center of the slot, which reduces the drift capacity of the panels, or even worse, the slots may already be exhausted, which leads to failures of precast panels, which was observed worldwide during recent earthquakes. The potential consequences of damage to the panel system comprise of economic loss due to repair, downtime, and interruption, but the collapse of panels create a life safety hazard, which stimulated the development of the panel system comprising of rocking connections. We can see here there's a panel with steel embeds at four corners of the panel and weld plates at the bottom of the panel. The vertical slots in the steel embeds allow the panels to rock while taking the outer plane loads, and the weld plates, which sit on bearing connections from the structures, transfer the gravity load from the panel back to the structure. The in-plane drift capacity of the panels is determined by the length of the slot and the aspect ratio of the panel. While manufacturing these connections, special attention was given to the details considering the smooth rocking of the panels, for which the face of the mild steel plate was grinded smooth. The threads of the bolts were kept outside the slot, and the slot was filled with grease. This was also to avoid the overtime corrosion of the slot. One of the main challenges while manufacturing was to parallelly align the vertical slots of the steel embeds, for which the steel embeds were first tack welded to angle lines, and the angle line was then connected to the formwork. This prevented the wobbling of the steel embeds during pouring of the concrete. Moreover, to prevent the clogging of the threads were taped. And to avoid the wet concrete squeezing in the slot, silicone and racks were used to cover the slot. The concrete was poured after the angle line and the weld plates were clamped into position. After the concrete cured, the angle lines were removed, which led to several dents on the surface of the concrete, which were later grouted smooth. Now the test setup consisted of a 3D structural frame, which was designed to deform under shear mode during the applied quasi-static cyclic loading following FEMA 461 protocol to a maximum drift of 4%. The test comprised of 3 sub-assemblies of panel pairs. The inline assembly allowed us to evaluate the in-plane performance of the panels. The inclined corner assembly allowed us to evaluate the bidirectional performance, and the return cover corner assembly allowed us to evaluate the performance of L panel at the corner of the building. The panels were 2 meter high and 120 millimeter thick, and the gap between the panels was kept at 25 millimeters. The panels were lifted using cranes and clutches into position, and plastic shims were used to maintain the vertical gap width. Sealant was then applied to the joints to a depth of about 15 millimeters. The panel structure connections consisted of top connection and bottom connection. The top connections consisted of horizontally slotted plate for tolerance through which the bolts from the panels passed. After the panels were into position, the washers were tack welded. Similarly, the bottom connections consisted of rectangular hollow sections welded to the beam on which the panels sat. The bottom connections also consisted of horizontal slots through which the bolts from the panels passed, and the washers were also tack welded. The precast panels rocked as expected, with no visible damage to panels and their connections. However, tear in sealant was observed during 3% drift cycle. Here we can see the rocking of the panel pairs in the inline assembly and in the inclined corner assembly. While comparing the system's performance with the traditional systems of horizontal slots and ductile rods, we can observe here that the rocking connections provide superior seismic resiliency, up to 4% intra-story drifts. From this research, it can be concluded that even though the manufacturing process of the panels comprising of the rocking connections require greater quality control and supervision, the installation of the panels is easy and quick. Moreover, the panels comprising of the noble rocking connections provide higher seismic resiliency while avoiding larger vertical gaps at building corners. I would like to thank all the funding partners and sponsors for this research. Thank you.